Presentation I gave after a hackathon sponsored by NASA on using their cloud platform, computing platform, to analyze or access and analyze remote sensing data that NASA has available in the Earth data cloud. This project is part of a longer-term project that I'm doing, trying to understand how coastal upwelling systems are changing around the world. Coastal upwelling systems are vitally important to coastal fisheries. There are reasons to think that coastal upwelling will change as the Earth climate changes, in particular as warming occurs. We have land warming faster than the ocean. That should change the winds, anticipated to change coastal upwelling. But also we have many other changes happening to the ocean. Also currents are changing and sort of localized, like warm blobs and cold blobs and that sort of thing changing. And those may be changing coastal upwelling systems also. This figure shows some of the major upwelling systems around the world. And there are two main types. Continuous means that upwelling is happening all year round, and that's the red ones. And the blue ones is systems where there is seasonal upwelling. So it is upwelling part of the year and not other parts of the year. The goal of this project was to explore getting an SST, sea surface temperature metric for upwelling automatically. So what I mean by automatically is I want something that I can basically just set an algorithm going, and it's going to kind of walk along these coasts and collect this sea surface temperature metric of upwelling. This is based on a prior year's work on developing this metric. So I'm not going to go into that, but just to say that it's a metric where I'm comparing the sea surface temperature near the coast and the temperature away from the coast. When upwelling is occurring, the sea surface temperature near the coast is colder. As I said, I'm using sea surface temperature for this project. And this is the basic idea here. I had done some previous work to develop a method by which I could get data points along the coast of continents and have those points equally spaced along the coastline, and then also get the point that is perpendicular to the coast but offshore by a certain uniform distance offshore. And I'm going to be looking at the difference between the temperature of the point that's close to the coast and the one that's farther away from the coast. That's the metric for upwelling. What this NASA hackathon allowed me to do was use their computational engines to get the data for all the years available. This is early 80s to 2021. Get it for all these points. You'll see there's a little over 550 points here. So a lot of points. This would take a really long time if I were doing this on a local computer. Okay, so what I'm going to show you are the results from this. And if you look here, you see these points along the coast are numbered. Okay, and that's what you're going to see on the x-axis. So I'm taking basically these numbers and I'm stretching them along the x-axis. And then on the y-axis, what you're going to see is if the coastal temperature is colder than the offshore by some threshold. So right here. So dark is when it is colder, so that would indicate upwelling. And the light blue is not upwelling. Now, there's one caveat. I didn't color the NAs, so the missing values, properly in this plot. So there are some regions where light blue is just a missing value. For example, it's ice. That's typically, this is all right here is, this is all up in the Arctic, and this is all ice. So now we're going to walk through this. So we're starting at 0. We're starting here, and we're going to be walking around, and I'm going to show you, highlight the major upwelling systems that occur around the Americas. So let's start here. So this is the Georges Bank. This is a current-driven upwelling system, and you can see it's kind of unique. It's the coastal area is always colder than offshore. So that was kind of strange. This is the Bering Strait. You can see it's a very small, short upwelling season. This is the Gulf of Mexico, very different. It's over many kilometers of shoreline and very stable. So upwelling's on, then it's off. Upwelling's on, and then it's off. South Caribbean, quite a bit different. This system, it's not really seasonal. And sometimes it's on, sometimes it's off, but there's not a really obvious seasonal pattern going on in the South Caribbean. This is a system off the east coast of Brazil. You see a very strong seasonal system here, but there's one that's a bit to the north of that that's quite a bit less seasonal. Okay, now this is one of the most famous upwelling systems in the world. This is the Humboldt current upwelling system off Peru and northern Chile. You can see this part right here. This is the continuous upwelling. But this is the northern part. If we look towards the south, we can see that part of it is seasonal. So it comes on, then it's off, and then it's on, and then it's off. So this is kind of interesting in Peru that part of it's continuous and part of it is seasonal. And now we see the Northern California seasonal system. Now here I'm just showing whether it's above some threshold or below. It makes it really obvious to see this seasonal pattern, but we can also look at the data and just look at the difference rather than having a thresholding. So this here is the difference between the nearshore and offshore. This blue color is where the nearshore is colder, and then these colors is when it is warmer. What you can see here, we can just see it really obviously with the Gulf of Mexico. You can clearly see that seasonality here. And let's see, I think this is California right there. You can kind of make that out. It's quite a bit harder to see though. Okay, so let's go back to here. What I have shown is that, yes, I'm able to get this sea surface temperature index, and I was able to do that for the Americas. I haven't tried that for the other continents. That's the next step. I did collect all the years that I had available. It's from the early 80s into 2021. So now I have a data set that I can begin to work with to analyze. And the next question I need to explore is, okay, how do I quantify what's going on with these seasonal upwelling dynamics? So, well, not really dynamics, just the pattern. What's going on with the pattern? And how can I ask, is it changing? I have two ideas that come to mind directly. And I think the first thing I want to try is using wavelet analysis to study this pattern. Now here you only see, what is this, 5 upwellings, but that's because I'm showing it just from 2016. I have many more years of data. So I have quite a few cycles to look at. So I think that perhaps wavelet analysis might allow me to get that at this. And in that case, I would take a slice through one of these. Whoops, here. And I'd actually not be using the threshold data. I'd be taking a slice through one of these here. Okay, but I'm gonna stick with this just because it's easier to see. But it's not 0-1 data I'm going to be analyzing. So that's the first thing I want to try, is explore wavelet analysis. I haven't worked with that before, so I'll have to learn a lot about it. The other idea is some kind of, maybe perhaps qualitative, looking at like the area here that is dark. You know, is the size of this changing? Perhaps I can, measure the center of gravity somehow. I don't know. I don't like that as much because it feels very ad hoc to me. So that's the next step that I have. However, I will say that this project was definitely a success because I now have a data set that I can begin to work with.